Welcome to the Refrigeration Lab presentation, contributed by Rahan, Stephanie, and Jeffrey. Guidance was provided by instructor Dr. McNair with assistance from teaching assistants Renan and Manu. The session will cover key aspects of refrigeration theory and experimental findings. Machine Chillers Inc. has created a new cooling system centered around a vortex tube with air as a working fluid for enhanced safety. An independent assessment of this system is underway by Birdle Inc., tasked with modeling the system and evaluating its performance. The device's primary aim is refrigeration, cooling an object through mechanical work. The key area of focus are examining how the compressor's ability to pressurize the system is affected by motor settings, analyzing the vortex tube's properties to understand the energy transfer rate based on temperature and mass flow rate, characterizing the heat and energy transfer at the insulated aluminum block, tracking the energy exchange from thermal load to air, and the influence of insulation on system energy. These efforts aim to thoroughly quantify the system's refrigeration capabilities. There are many key components for this experiment, starting with compressor and motor. The compressor, driven by an electric motor, is responsible for pressurizing the air needed to initiate the refrigeration cycle. The heat exchanger, this component cools the pressurized air down to ambient temperature as it passes through, preparing it for a refrigeration process. Accumulator tank. Functioning as a buffer, the accumulator tank soothes out pressure variations from the compressor, providing a consistent airflow to the vortex tube. Vortex tubes. This splits the air into two streams, segregating into hot and cold flow based on temperature. Flow sensors located at the exits for both the hot and cold air streams. Flow sensors measure the respective mass flow rate. Pressure sensors are strategically positioned at five measurement stations. These sensors track pressurized levels within the system. Temperature sensors are crucial for gauging the temperature at various points, including the input and output, as well as the ambient and load temperatures. The aluminum block integrated into the system acts as a thermal load and is cooled down by the air from the cold stream. And insulation surrounding the aluminum block. The insulation is meant to reduce heat transfer with the surroundings to ensure precise thermal measurements. The depicted cycle starts with a motor-driven compressor that elevates the air to a high pressure and temperature. This air then sheds to the hot reservoir via heat exchanger. Following this, the air enters the turbine where the vortex tube effect reduces its temperature as the pressure drops. The cooled air absorbs heat from the object being cooled in the second heat exchanger, completing the cycle and maintaining the desired cooling effect. The refrigeration cycle operates under an energy balance equation. In the initial assessment, the heat of the air denoted as Q. Air is understood to be the sum of two components, the load heat, Q load, and the ambient heat, Q amp. In steady-state energy balance, the equation is modified to exclude the load heat as indicated by the red cross over the term. This exclusion reflects the condition under which the system has reached equilibrium and the only ambient heat is considered. The cycle's operation, characterized by the sequential increase and decrease of air pressure and temperature, facilitates the transfer of heat from cooled volume to the environment. This mechanism is central to the principle of refrigeration.
For the experiment, several sensors were used to characterize the different subcomponents of the system. The measured values include temperatures, pressures, and mass flow rates. Due to sensors having irregularities when measuring, an offset must be calculated to ensure the recorded data is as close to the true value in the system. Presented is the found offset equations used for calculations. All calculations were taken at 0 psi to provide a basis for comparison. The offsets for each value will later be subtracted from each of its corresponding values at different pressures to obtain the true experimental value.
On the left, motor voltage is plotted against pressure out of the compressor P3. As you expect, increasing motor voltage increases pressure. This is because the motor is acting as a compressor, and increasing voltage increases RPM of the compressor. However, we observe the trend is nonlinear as the pressure increases, as the pressure reaches around 6.15 times 10 to the 5th pascals. This is expected since the compressor is more likely to leak and have lower efficiency at higher speeds. Similarly, on the right, we see T1 plotted against input voltage over P3. T1 is the temperature of the air leaving the compressor. It is clear that increasing the motor voltage and therefore pressure increases the temperature of air coming out of the compressor. This is standard for compressors to heat up the air output as it is pressurized. On the left, we see that T3 also increases with motor voltage. T3 is the temperature of the air exiting the accumulator tank, which is passed through the heat exchanger. This shows that the heat exchanger is limited in its ability to cool the pressurized air to ambient temperature. Ideally, the air temperature exiting the heat exchanger should be ambient. The plot on the right shows T3 compared to T1 before the heat exchanger, where you can visualize that the heat exchanger has cooled the air significantly but not perfectly. This will affect the vortex tube characterization as hotter air is flowing through it at higher pressures. These plots characterize the temperatures of the air exiting the vortex tube. On the left, we see that the temperature exiting the vortex tube on the cold side decreases to a certain point before slightly increasing. This visualizes the optimal operating pressure at which the vortex tube can minimize the temperature of the cold and hot air at about 5.8 MPa input pressure. On the right side, we see that the increasing pressure increases the hot air temperature. This temperature is less relevant as the air is exhausted from the system. These plots characterize the mass flow rate of the air exiting the vortex tube. We see that the mass flow rate exiting the vortex tube on the cold and hot side both increase with increasing input pressure. This is as expected. Interestingly, the hot air flow rate is slightly higher across the pressures. This is likely due to the vortex tube's internal mechanism of separating hot and cold air.
The system's heat transfer was observed under steady-state conditions. The energy balance for defining the heat rate for the air using experimental values is defined in equation 1. The range for experimental heat transfer was found to be between 0.6 to 1.4. These ranges were later compared to the theoretical heat rate using equation 3. The range for these values were between 0.15 and 0.7. Both the theoretical and experimental thermal resistances were calculated using equation 2 for experimental value and equation 4 for the theoretical value. As seen, the values of the experimental changes with voltages. This is due to resistance relying on values such as T5 and T4C, which would change throughout the experiment. Lastly, the experimental thermal conductivity was calculated by manipulating equation 4 with the experimental thermal resistance. It is shown the value is inconsistent throughout each trial and seems to have an inverse relationship with voltage. It also shows the conductivity should be calculated as the experimental value overshoots the initial value used, which was 0.033.
This summary outlines the initial experiments, which determined the steady-state performance of the vortex tube and defined ambient heat. The results were compared against theoretical predictions, accounting for variable input pressures and uncertainties. Future experiments will explore transient heat transfer and the role of Q load. The aim is to enhance understanding of the system's efficiency in cooling the load.